You're also not that far away. Now we all learned that he doesn't use Opera. Okay, so these are our equations. The electric charges exist, point charges exist. Magnetic point charges do not exist. Changing magnetic field creates an electric field. Currents create a magnetic field, but also changing electric field creates a current. Now we have a new source of the magnetic field. A changing electric field will create a magnetic field. Now let's do a simple example first. Okay, here we said that, okay, this capacitor was in the Andromeda galaxy, but let's just imagine we have another capacitor right over here. What is the magnetic field inside our capacitor? Well, you see, this term over there, this term over here, it just behaves like a current in the sense that it creates a magnetic field. It acts as if, I'm not saying that it is, but it acts as if the current doesn't stop over here, but continues, but not in the form of moving charges, but in the form of changing electric field. It just acts like that. The charges, when they reach over here, of course they stop here. There are no charges moving across my capacitor. They are just accumulating at these plates, but this changing electric field acts as if it is just a different kind of current. Not a current created by moving charges, but a current created by changing electric field. And that is why it is called the displacement current. It just displaces ordinary moving charges, in a sense. Now let's look at the electric field, the magnetic field created by this moving, changing electric field. So we will imagine we have a capacitor. Let's say this is charge plus Q, the other plate is charge minus Q. We have electric field lines going from the plus Q to the minus Q plate. We will just assume that Q is changing in time. Now let's just assume we have a different view of this one. The plates are circular. Just for simplicity, we will be assuming that they are circular plates. And let's say with this view, the electric field line is pointing towards you. The electric field is uniform. It's pointing towards you. Now, first of all, what is the direction of the magnetic field lines? Just use the right-hand rule. You see, we said that the electric field just behaves like a current. It is as if there is a current running in this direction. So the magnetic field lines, depending on the direction of this current, whether it is coming here or that way, they will be more or less circular. Well, the plates are also circle. That also tells us that if we rotate our system around this point, around the center, nothing should change, including the induced magnetic field. So the only possibility left is that the magnetic field line should be just circular, just like an infinite wire. So these can be the magnetic field lines. We don't yet know their direction, but we can just pick up one direction to be the positive direction of the magnetic field. Now let's just imagine this circle over here, this one, inside my plate. I know that B is in that, let's say that dl is in the direction, let's just call the direction of dl my theta hat. I mean, at this point, it will be pointing in this direction. At this point, it will be pointing in that direction. We said that the magnetic field is circular, so B will be also pointing in that direction, either in that direction or in the opposite direction, depending on the value of B. Furthermore, I also know that B can only depend on the distance from the center. It only depends on the distance. Now let's evaluate B dot dl. Well, this will be just B and dl if you just take their scalar product. It is just Br times dl. Br is just constant because over my loop, R is just constant, so I can take it out. What remains is just 2 pi r. Now let's look at the other side of my equation. B dot dl should be equal to mu0 I. Well, this I is, by the way, passing through the surface that you choose. Plus epsilon 0 d phi E by dt. Yep. Well, the problem is, what do you mean by enclosed? What do you mean by enclosed by the loop? What do you mean by inside the loop? No. In a sense, you choose it. But what you mean by the inside of a loop is that if this is your loop is the boundary of a surface. And the enclosed current is nothing but the current passing through that surface. So that is why here I have this, the current passing through the surface. Which surface? Well, there are infinitely many of them you can choose from, any one of them. Also here, now one of your friends had a nice point. This I over here in this equation is not equal to this I in general, for a general surface. That I is the I passing through your surface. Now, if you choose this surface, then that I is 0. If you choose this surface, then that I is just this I passing through the surface is this I over here. Now, let's continue our problem. Now, we can just imagine this plane surface bounded by my ring. There are no charges moving through that surface. So this is just 0. But this need not be 0. Since we are assuming the electric field is uniform, this is equal to mu0 epsilon 0 pi r squared times E. Is it plus E or minus E? Plus E, because if you just imagine, this is my loop. You just choose your right-hand rule. This is the direction of positive flux. If the electric field is pointing in that direction, more or less, then the flux is positive. If it is pointing in the opposite direction, then the flux is negative. So in this case, the flux is positive. Well, then this has to be equal to this one. And that gives us the magnetic field at a distance r from my plate. This is equal to mu0 epsilon 0 pi r squared E divided by 2 pi r. Well, sorry, there is a d by dt over here. We can make some simplifications. This is mu0 epsilon 0 over 2 dE by dt times r. So the magnetic field is increasing as you go away from the center. There is zero magnetic field at the center. As you go away, the magnetic field increases linearly. Now let's determine the magnetic field out of my capacitor. Well, here there is not really a capacitor, but we are just imagining that we have a region of space where we have a uniform electric field in a finite area. In this area, the electric field is changing. So since there is a changing electric field, there will be a magnetic field created, and we had calculated the magnetic field in this area. There will also be a magnetic field created out of that area. And the magnetic field to calculate the magnetic field created out of that area, well, this result doesn't change. We are just using the fact that the magnetic field lines are circular, and they only depend on the radial distance. What will change will be this one, because the electric field is non-zero only in this area. So the total flux will be just that the total area of my capacitor times the electric field. This is if R is less than the radius of my capacitor. If R is larger than the radius of my capacitor, 2 pi R times BR will be the same. It won't change. This should be equal to mu0, epsilon 0, d by dt, A times E. A being the total area of my capacitor. The magnetic field at a distance R will be equal to mu0, epsilon 0 over 2 pi R times A times dE by dt. Well, let's do one more thing. This is equal to mu0 over 2 pi R d by dt epsilon 0 A. What is the electric field in a capacitor? What is area times sigma? The total charge of the capacitor. But this is nothing but I. So basically, out of the capacitor, it is as if the capacitor is not there. It's as if the current is just continuing straight forward. Inside the capacitor, it won't be, well, now we can talk about inside the capacitor, and there it will be just increasing linearly with the radius.
I'm sorry, could you explain again what is displacement current?
Now, any questions on this one, then we will go back to the displacement current. So basically what we had done when we were calculating the created electric field by a changing magnetic field, we are just repeating the same thing. Now this time we have the changing electric field which creates a changing magnetic field.
Lineer olarak değişiyor içinde. Dışında da kendi aynı şeyi içeride. Çünkü orada da
So it just goes to zero as the rate as the distance. So it's basically, if you just draw the magnitude of B of R as a function of R, it just increases linearly first and then goes to zero. And it is continuous. Now, what is the displacement current? Now, basically this one. What we had seen was we had to modify the Ampere's law by adding this term. This term kind of behaves like the current, so that is why we just give it a special name called the displacement current. How does it behave like a current? Well, there's no current in this region between the plates, but there is a changing electric field, and that changing electric field just behaves like a current. So a displacement current is, you can just think of it as a current, not in the sense of moving charges, but in the sense of a changing electric field. That's what we call a displacement current.
Can we somehow define the direction of this displacement?
Sure, the direction is in the same direction as the current. You see, the displacement current, we had defined it as epsilon 0 d phi E by dt, which is epsilon 0 d by dt of the integral of the electric field over our surface, epsilon 0 dE by dt dot ds. So we can, well, you see, the current has a direction, is not a vector. So it doesn't really have a direction. It's the current density that has a direction. And the displacement current density is this one. This is our displacement current density.
Exactly.
Exactly, that's the definition. That's how we define it.
Hocam orada neden direkt D'yi niye orada direkt D'yi kullandınız zaten? Gram radyans.
You mean the partial derivative, not the total derivative. You see, this, when you take the integral, this integral depends only on time. But electric field depends on time and also the position. Okay, so inside this capacitor, I mean, we will not be proceeding that line of thought, but let's see. We had inside the capacitor, there we created a magnetic field, which is changing in time, and that change is given by this expression over here. So it depends on the electric field. And, well, if the current is constant, the rate of change of the electric field will be more or less constant, so that's it. But if the current is not constant, the rate of change of the electric field also will not be constant. So this will depend on time. But if it depends on time, that means the magnetic field will also depend on time. So we have a time-dependent magnetic field, but we already know that time-dependent magnetic fields create electric fields. So there will be an additional electric field created due to this time-dependent magnetic field. And then, of course, the additional electric field will have time dependence, and you have to count that. So since it is time dependent, there will be a magnetic field created, and you can go up to infinity. Now let's do another example. Now, if you have noted, we never talked about the magnetic field created by a moving charge, a point charge. We never talked about that up to this point, because it was not magnetostatics. Even if the charge is moving at a constant speed, constant velocity, it's not a magnetostatic problem because our system is constantly changing. We always talked about magnetostatic cases where, although we had currents, the currents were not time dependent. A moving point charge is a time dependent current. So what is the magnetic field of a moving charge? So first approximation, let's say. So here we have this charge. It's moving. Let's say with a given velocity v. No? When did we talk about it?
We said that the moving charges create magnetic field.
Okay. That's all we did. We said. We didn't say how much. What is the direction of that magnetic field?
Just imagine this as a like a current, for example.
but it's not a time-independent current. On the average, maybe, but on the average, the current will be 0 anyway.
But if we set it up on a ring,
On a? Okay,
it would be 1 electron in, current wouldn't be 0.
okay. But it's not a ring.
Can we calculate it that way?
Let's see. Let's look at the electric field here. Is it changing in time?
Yes.
So that will create a magnetic field. What is the electric field over there? Let's say this is at the time when the distances are. The electric field, let me add this 0 over there. 1 over 4 pi epsilon 0, q over r squared in the r hat direction. I will tell it in a moment. Now the problem is, we derive this expression assuming electrostatics. Now we have a magnetostatic problem. No, not an electrodynamic problem. Things are changing in time. So we don't really know whether this will be true or not anymore. But there is one thing we know. The electric field, the total electric field, should be equal to that one if V is 0. So if V is 0, the electric field should be equal to 0. It's equal to this one, if V is 0. So the total electric field will be basically some E0 plus, let's say, E1. Just imagine doing some Taylor expansion. You can say that this depends on V to the 0. This is proportional to V to the 1. The next one will be proportional to V to the 2, etc. Now, we will do a similar thing for the magnetic field. B0 plus B1 plus B2. Now, what is the magnetic field if the charge is not moving? It's just 0. B0 is 0. So if the charge is not moving, there is no magnetic field anywhere. Now, if the charge is moving, E0 will be changing in time. But if E0 is changing in time, it will create a magnetic field, which will also be changing in time. But a changing magnetic field will create an electric field, which will also be changing in time. And that changing electric field will create another magnetic field, and so on and so forth. Now, you can actually do this calculate this exactly. We will be discussing the exact solution at the end. But for the time being, let's just try to calculate what this B1 is, the term proportional to the velocity of the particle.
What does this 1 into brackets mean?
Now, let's say Bi is proportional to V to the power I. Or Bn is V to the power n. That is what I mean. It is proportional to speed raised to the power n. This term is proportional to the speed. This is proportional to speed squared. The next one is speed cubed. Have you studied Taylor expansions? Okay, finally, yes. Just imagine this is our Taylor expansion in speed. I'm just making a Taylor expansion in speed of both the electric field and the magnetic field. Now, of course, we will be using the Ampere's law to calculate the magnetic field. And Ampere's law, of course, we first have to imagine some circle, some closed loop. So what do you think would be the direction of the magnetic field lines? I mean, some of you already had an answer. Let's say you can just imagine this as a current. And even an infinite current time-dependent one and position-dependent one. The right-hand rule. So if it's a positive charge, this will be the direction of the magnetic field lines. So basically, we can imagine the magnetic field lines will be circular, so we can just imagine a circular loop. So we know that B dot dl around this loop, since the problem also has this cylindrical symmetry. If I rotate my system around this axis, nothing changes. So that also tells me that the magnetic field lines should be circles. Now, if they are circles and they only depend on the distance, well, they will depend on z. Let's say this is my z-axis. This is x and y. Let me just call this r, that distance. Now, the magnetic field will depend on r. It will also depend on z. I don't know the dependence, but it will have a z dependence. That I know. But neither r nor z changes around my loop, so I can just take it out. So what remains is b times b at the point rz, the magnitude, times 2 pi r. This is the b dot dl integral around this loop. Now the current, writing the current, the current is kind of complicated because for a general surface, there is no current running through that surface, but there is an electric field running through that surface. What is the flux going through that surface? Electric flux. First of all, which surface do you think we should take? I mean, we should choose a surface whose boundary is this loop, whose edge is given by this loop. So which surface do you think we can? Cylinder. It will complicate our calculations.
The surface should be such that the electric field must be perpendicular.
Spherical, the easiest one. So this is our surface. A spherical surface whose center is at the position of my charge. Now this is a circle. Let me just draw it like this. Here I have my point charge moving in this direction. And I'm interested in the magnetic field at that point. So what I do is I imagine a surface, a sphere, like this. And this is my loop. Well, the nice thing is, for this sphere, B is parallel to E is parallel to dA. dA is just in the radial direction. Electric field is also in the radial direction, at least no, it's in the radial direction. It's also uniform. So we can just integrate it. We have to evaluate phi E will be just E dot dA. On the surface, the magnitude of the electric field is constant. It is 1 over 4 pi epsilon 0 Q over R squared dA. What is that area? Let's say this angle is, let's say, theta 0. Does anybody know that area? Let me just imagine, well, this is my area, right? I'm just looking at it from here. This has this curvature. This is my part that I want to calculate. I can just imagine it. You mean like this? Ring. Now, I will cheat a bit, in the sense that you are already getting bored, right? I don't want to spend so much time on these integrals. This is equal to 1 over 4 pi epsilon 0 q over r squared. Now, this is r squared sine theta d theta times 2 pi from 0 to theta 0. Now, why is it so? I mean, if you don't know, just ignore it. Just trust in my final answer. It is q over 2 epsilon 0 r squared. Then well, these r squares, they cancel. I have 1 minus cosine theta 0. So this is phi e. What is time dependent over here? I have to take its time derivative. Theta 0 is time dependent. You see, as this particle is moving, this ring is fixed over there, so the theta 0 will get larger and larger and larger. d phi e by dt, this is equal to q over 2 epsilon 0 sine theta 0 d theta 0 by dt. So that's the last part which we have to evaluate. What is d theta 0 by dt? Well, it will be related. Let's look at this one. Sine theta 0 What is sine theta 0? Let's say this is the distance d. This is r. D is constant. So sine theta 0 is d over r. Do you see it over here? I have this. Here I have a ring. This ring has a radius d. No. That ring has a radius r. That was our definition first. So this is 2 pi. Let us change that to d. I want to keep r to be the radius of my sphere, the distance of this point from my point, from the charge. So sine of theta 0 is just d over r. It is the radius of this ring divided by this distance. That is the sine of theta 0. Just take the time derivative. Cosine theta 0 times d theta 0 by dt. This is equal to minus d over r squared dr by dt. R is time dependent. dr by dt is not the velocity, by the way. But we know that r, let's say this distance is x. R is square root of x squared plus d squared. Now here I started with sine theta is equal to d over r, took its derivative. I got this one. I know what r is. R is this one. Just take the time derivative. This is equal to minus d over r squared. Well, d is constant, so the time derivative, take the derivative with respect to x. That gives x over square root of x squared plus d squared times dx by dt. What is dx by dt? Minus v. You see, this is my x. If v is positive, x is decreasing. That is why I have a minus sign. So cosine theta d theta 0 by dt This is equal to, this is minus V d over r squared. You see x over x squared plus d squared. This is nothing but cosine theta 0. Why? That is basically, x is this length over here. The other one is r. X over r is cosine theta 0. So cosine theta 0s, I can just cancel them. So we have the rate of change of theta 0. And we have the rate of change of the flux, electric flux. This is equal to Q over 2 epsilon 0 V times d over r squared times sine theta 0. Okay, now let's combine everything we have. On one hand, we had calculated that B dot dl is B times 2 pi d. This is B dot dl. On the other hand, we know that this is equal to mu 0 epsilon 0 d phi E by dt, which is equal to mu 0 q V over 2 epsilon 0 d over r squared sine theta 0. Okay, we have another epsilon 0 over here. Well, epsilon 0s, they will cancel. So we have B is equal to mu 0 over 4 pi q V d sine theta over r squared. This is the magnitude. Let's write it in a different form, which might be a bit more familiar to you. These, yes, these they also cancel. You see, this was our problem. We had a charge over here moving with a velocity v in this direction. And we were looking at the magnetic field at this point, given by the vector r. And we first said that, okay, the B is also positive. We had defined the positive direction of B at that point to be out of the screen. We also found the component to be positive, so B is in this direction. That we also know. This angle over here is theta 0. That's how we had defined theta 0. Now let's look at this one. Well, we have V is a vector, right? So here we can put a 1, which is the magnitude of another vector, unit vector. And then we have a sign, which reminds you. Let's look at the cross product of r hat cross V. What is the magnitude of r hat cross V? Magnitude of r hat is 1. Magnitude of V is V, sine of theta 0. Magnitude of r hat cross V is nothing but V sine theta, theta 0 over here. What is the direction? R cross V is into the screen in the opposite direction. So if I just change the order, B is equal to mu 0 over 4 pi Q times V cross r hat over r squared. This is the magnetic field created by a moving charge. To a first approximation. Remember, we said that this is nothing but the first approximation. Because as the charge is moving, magnetic field is also changing, So this changing magnetic field will also create another electric field, which will modify the original electric field we had. The electric field will not be of this form. Now let me draw the electric field lines of the exact solution. Now we will not be discussing the exact solution. But if you have a point charge over here, moving with a velocity v in this direction, the created electric field lines do not spread over a sphere uniformly. They look like this. They are not so dense in the direction of propagation or in the opposite direction, but they are very dense on the perpendicular direction. These are the electric field lines. Wait 2 more years. Or not, maybe not even 2 more years. Next year you will be taking modern physics. There you might be covering part of it. They will be circular. They will still be circular. But of course, since the electric field line is stronger over here, the rate of change of the electric field at these regions are stronger. They will be stronger at these regions. The magnetic field will be weaker in this region. True. Correct. Well, you see, what happens is you can start from this law. You see, Q times V is nothing but your current. Current times dl, let's say. From this law, you can obtain the Biot-Savart law from this expression. Just sum the contributions of various charges. If you have, a current is many charges in motion. If you just sum the contributions of all of them, then you obtain the Biot-Savart law. And it's interesting also that you see these additional terms. There are also these additional terms to the magnetic field. They cancel in that sum if you assume a uniform current. So Biot-Savart law is exact. Although this one, this expression that we derived over here is not exact, Biot-Savart law is. Now, before you go, I want to discuss just a couple of more points. Some of you were asking this question before, if you remember. Just imagine 2 charges. They are moving in the same direction. Now, this was the question. We can go to a reference frame in which both charges are at rest. So it's an electrostatic problem, so they will be exerting an electric force on each other. It's just that in that reference frame, it's electrostatics. Now let's see what happens in this reference frame, though. This is a moving charge. It will create a magnetic field at the position of the other charge, and the magnetic field will be more or less like this one. Now, what is the magnetic field created by this charge at this point? Well, if we are looking at the magnetic field there, this is our R. So what is the direction of the magnetic field? V cross R is out of the screen. Now, we also know the Lorentz force. What is the direction of the magnetic force that the above charge will feel? V cross P is downward. This is the magnetic force that that charge will feel. Now the question was this one, I don't remember who asked it, but if the electric field is not modified, if the electric force is the same, now there is an additional magnetic force, but this additional magnetic force means that the acceleration of this charge will be different in these two reference frames, which shouldn't be. The acceleration should be independent of reference frames. The electric force increases. Why? Just look at this graph. The density of the electric field lines in this place is larger if the velocity is large, if it is moving with a velocity v. So the electric field is stronger, so the electric repulsion is stronger. So in this reference frame, there is a stronger electric repulsion, but there is also an attractive magnetic field. And hence, in both reference frames, you see the same acceleration. Let me just do one more. Yes?
Is there illusion or something we prevent happens to explain?
What do you mean by illusion?
I mean, still,
It is the predictions of the laws that we have.
so it's a prediction
Yeah.
we made of kind of.
Well, the laws are kind of, we made them up all.
Because it's kind of, I don't know, it's weird.
Well, let me first say one more weird thing, and then we can all go. Let's just imagine these two charges. Now, you had already said that this above charge, the magnetic field created by the lower charge, will be out of the screen. What is the direction of the magnetic force?
Right.
To the right. Now, what is the magnetic, well, let me put it somewhat away. It is over here. Now, what is the direction of the force, the magnetic field that this charge creates at this point? Remember, its direction is V cross B. Yeah, over here. V cross R. So this is my R. This is moving in that direction, V. So V cross R into the screen. At this point, there will be a magnetic field created into the screen. What is the direction of the magnetic force? Upwards. So we have these two charges that are exerting forces on each other. But these forces, well, we didn't check the magnitudes, but definitely they are not opposite to each other. They are not action-reaction pairs. Remember Newton's third law. Newton's third law states that all the forces, if an object exerts a force on another object, then that second object exerts a force on the first one whose magnitude is the same and whose direction is opposite. This definitely doesn't satisfy that. But then we have another problem. Newton's third law tells us that momentum is conserved. Because since these forces are pointing in opposite directions, the momentum gained by one particle is lost by the other one. So the total momentum of our system is conserved. But now, since we don't have action-reaction pairs, the momentum of these two charges, the sum of that momentum is not conserved. Anyway, those we will continue next week. So now I give you an incentive to join my lectures on the last week.